All right, so with that in mind, let's try another one and just talk about the bigger picture and kind of the overall general strategy here. So for all of these, the first step is to solve each of these inequalities. Once you solve the inequalities, then graph them on the number line to see where they overlap or even if they overlap. And then lastly, consider whether you have an or an and statement. So let me write this strategy down so that you have it. So like I said, the first step is to solve both inequalities. Likewise, our second step, once we've solved both inequalities, is to graph them both on the number line. And our last step, once we've graphed the inequalities, is to consider whether it's an and or an or statement. So let me just briefly write that down. So this third step is usually the trickiest part for students. And I'll be honest with you, these compound inequalities are some of the most difficult exercises for students. For some reason, they're just incredibly challenging. But if you learn the strategy and you practice this strategy over and over again, it will simplify and organize these problems greatly. It's only when students approach these without a strategy that they tend to get lost. So what do we mean by these and or statements? So let me write kind of the definition for each of them. So an and statement means that it satisfies both inequalities. So an and statement satisfies both, but an or statement, we can say, satisfies at least one inequality. So it doesn't have to satisfy both like the previous example showed, it just has to satisfy at least one of them. So this is kind of the big picture. We're going to solve the inequalities, we'll graph them both on a number line, we'll see where they overlap, and then we'll consider the and or the or statements. So for this one, we're dealing with another or statement, so we know that once we solve the inequalities and we graph them, that the values in our solution would satisfy at least one of the inequalities. And it is possible to satisfy both of them. That's okay too, because technically it would be satisfying at least one of them. But for an or statement, it really only has to satisfy one. It can do both, but it doesn't have to. So let's jump into this problem. And for these problems, we're going to do a lot of examples because I think the more that you see, the more obscure examples you see, I think the better. So we'll try and look at all the cases, and likely this will be 2 or 3 videos long. But let's try this problem. So let me scroll over, make a little bit of room here, and we're just going to follow that strategy. So let me first solve both inequalities. So let me write them down. We got minus 6x plus 14 less than minus 28. And our other one, I'll use a different color for that. We'll do 9x plus 15 is less than minus 12, or less than or equal to minus 12. It's very important to include that equal sign if it is in the original problem. So now we move on to the blue equation, the first one here. And we want to isolate the x term, so we got to cancel out the plus 14. So we'll subtract 14 on each side. So we get minus 6x less than minus 28 minus 14. So we're going more negative, and that will bring us to minus 42. Now we divide by a negative number, and this is the only difference between inequalities and equations, is that when you divide or multiply by a negative number, you have to flip the sign. So minus 6 divided by minus 6 is just 1. So you get 1x is now bigger, and minus 42 divided by minus 6, the two negatives cancel, and you get 42 divided by 6, which is just 7. So in this case, x is simply bigger than 7. And now we'll try this one. So let me change colors again. So we want to isolate the x term, so we'll subtract 15 on each side. So these cancel out. You get 9x less than or equal to minus 12 minus 15 will bring us to minus 27. And now we divide by 9. And since we're dividing by positive, we don't have to flip the sign. So even though this number is negative, it's only when you divide by a negative or multiply by a negative that you have to flip it. So 9 divided by 9 is 1, or 1x, less than or equal to minus 3. So we've solved both inequalities. Now we go to the step of graphing them on a number line. So let me get a line going. And you don't have to write out every number. It's kind of whatever you're comfortable with, but I usually put 0 just as my reference, and I'll usually put these values. So 7 somewhere over there, and we'll say -3 is about there. And so for this one, this pink one here, x is less than or equal to -3. So we'll actually put in a filled in circle, and then it's all values less than that. So all values in this direction. Now this one, this orange one here, all values bigger than 7 satisfy this. So numbers like 8 and 10, 115, and so on. And we're going to do an open circle because it doesn't include 7, since we don't have the equal sign. So it's all values bigger than that. And now we want to consider the and or the or statement. And in this case, we have an or statement. So that means it has to satisfy at least one of these. So basically, when you're going through your number line, you're looking at individual numbers, like take -4. And you're asking yourself, does that satisfy at least one of these? And since -4 would satisfy this inequality, and we only have to satisfy one of them, -4 would be in our solution set. Likewise, if I look at a value like 8, 8 solves this inequality. And since we only need to satisfy one of these, 8 would also be in my solution set. But values in the middle here, like let's say 1 does not satisfy this one because it's less than 7, and it's also bigger than -3, so it doesn't satisfy this one. So all values in this middle region are not part of our solution set because they don't satisfy either of these. So one thing you can do is kind of divide your number line into regions. So region 1, where it's just this one, region 2, where it's neither of them, and region 3, where it's just this orange one here. And then you can go through each region and see if that's part of your solution set. So all of region 1, all values less than -3 satisfy this one, which means that they're all part of our solution set. Likewise, values bigger than 7, so all of these, they satisfy this one. And so all values of x bigger than 7 also would be part of the solution set since they satisfy this one. But values in the middle in region 2 do not satisfy either of them. So between -3 and 7, essentially, not including -3, all of those values are not part of our solution set. So when we build our solution set, they should not include from -3 to 7. But again, not including -3, just all values bigger than it. So we know that we're looking at x values less than -3 and x values bigger than 7. So that would be this one right here. Let me change colors. I had white going. So x is less than -3. That all satisfy this one. And x is bigger than 7. They all satisfy this one.